we have Dr. Prashant Patil. Uh, from IIT Guwahati. So, he is going to talk about challenges for automated application and solutions. So, before he talks, I would like to introduce him. So, Dr. Prashant Patil is currently working as an assistant professor at Mehta Family School of Data Science and Artificial Intelligence, IIT Guwahati, India. Before that, he worked as postdoctoral researcher at Deccan University, Australia. He has completed a PhD degree from the Department of Electrical Engineering, IIT Ropar, India. He has 2.5-year research experience as a postdoctoral research fellow. He has published his research work in the reputed journals like IEEE Transactions on Multimedia, IEEE Transactions on Image Processing, IEEE Transactions on Vehicular Technology, IEEE Transaction on Intelligent Transportation System, IEEE Signal Processing Letters, IEEE Transaction on Emerging Topics in Computational Intelligence. Also, his work got published in reputed conferences like CVPR, ICCB, ECCB, WACB, ICIP. His research interests are computer vision, deep learning, image, video, resource object detection, segmentation, depth estimation, activity recognition. So thank you for joining this session, sir. So now the session is over to you.
Yeah, thank you. And how much time I have?
1 hour.
Yeah. So I will try to cover all things in 1 hour. Okay. Hope my screen is visible.
Yes, sir.
Yeah. So very good morning, all of you. I think some candidates are joined online also, and some are offline. So good morning, everyone. In this talk, first of all, I would like to thank Dr. Rakesh to give brief introduction about my. And now I will try to cover like challenges for automated applications and solutions. So I'm Dr. Prashant and working as a assistant professor at IIT Guwahati. So what are the video-based applications? If you see that this is the one of the famous application like automated video surveillance system. Next one is automated traffic monitoring. Next one is automated driver assistance system. So these are the some typical applications of video. Means like whatever data we have recorded in video case. So these are the some applications. So what like these applications expects the clean data as the input means like wherever they want like they are processing the input means like video, so they are expecting that that data should be clear and heavily depends upon the subtask like object detection or object segmentation. So we will try to cover first, I will try to cover the what are the challenges for these applications, and then I will try to cover one or two solutions for that. So what are the basic challenges? Like one of the challenges that camera jitter. This is the recorded. This is the video recorded with a static camera. But if you see this red bonding box, in that red bonding box, that content or that pixel information is changing every frame. So that time it's very difficult to identify the this is the region of interest or not. Means like it will disturb the things. Similarly, dynamic background. In the dynamic background, if you see this green box is our region of interest. Mean that is like that object we need to detect or we need to analyze for the automated case. But in this in this red bonding box, if you see that water fountains having different heights, but that is not our region of interest. So that we need to neglect or we need to ignore in the high level processing task for that effectiveness of the or effective working of the applications. So next one is that illumination changes. If you see the t plus 10 and t plus 20 frame, that illumination is changing, because if you see first frame is having uh, first frame is having 10 5 lights on, like next frame only one light, also like next frame only one light, but that illumination is going to change. So in this case also our automated application should not uh, suffer from less performance. It should able to perform well in that case also. So in camouflage, if you see here, that person wearing the jacket, the color of the jacket and the color of the door is same. Similarly, if you see this one in this green box, that one aeroplane is there that is landed and it's coming to required gate. But if we are not able to see that uh, uh, plane, similarly that goat is walking on the stone. If you see that goat is walking, but we are not able to see with the naked eye. So in that case, our object detection algorithm, or like wherever we are mounting these applications should able to identify that objects, where even though it is a transparent or even though it is not visible to naked eye. Similarly, next one is a challenging weather. Whatever I discussed, that there these applications are expecting the clean data. So if you see in this case, clean data is not getting, because if you see the red box and if you see the red box in this frame, the two small cars are there. That cars are not visible, is visible. So shadow case also means like whenever objects are moving, so that shadow also moving. So in that case, that our algorithm or like whatever pre-processing we are doing, in that pre-processing we need to nullify, or we need to neglect that shadow portion, and we are able to provide the information about the only the moving objects without shadow. So this is the shadow and challenging weather case. Next one is the night videos. As we know that in night case, visibility is very less. If you see this, only that light is visible of that car, but that is a bigger car, so we are not able to see that car. So this is the problem with the nighttime video. And uh, this is the like one of the additional challenge as compared to the daytime applications. And intermediate means like some objects are standing for some duration. Like whenever we are in traffic, so that time whenever red signal is there, that time we have to stop the car for like 30 seconds or 1 minute. So in that duration also, our objects or whatever algorithm or whatever camera are mounted on the traffic monitoring system, that traffic monitoring system is able to identify or able to detect that objects is a region of interest, and it is not a stationary object. So these are the some object challenges. And next one is the turbulence. Turbulence is the majorly used in like military case, because that is a long distance surveillance. Turbulence video or turbulence case, turbulence challenge will come whenever we will record the data from the very long distance. So this is like one of the challenge. And next one is the bigger moving, means like sometime object may come like in entire frame, that object will be there. So in that case, how to detect or how to pre-process that, or how to pre-process the frame, so that we are able to show the particular region of particular objects, like region of interest object. So these are the major challenges in automated surveillance. So next, so that researchers started working on how to give the effective input to these kind of applications. So these kind of like applications, like automated surveillance or traffic monitoring case, we are like one in general application started for like moving object segmentation. Means like moving object segmentation means uh, we will like divide the each frame into two parts, means like background or foreground. So that background and foreground part means like foreground is our region of interest and background is not our region of interest. So this is a so the researchers started working on moving object segmentation task. So moving object segmentation, what is like exactly meaning by moving object segmentation? So in that moving object segmentation, generally three basic steps are there. In that, if you see for any video, they will estimate first background, then they will estimate the saliency, and then they will estimate the foreground. So this is the like background foreground segmentation. If you see this part, This is our, like, whatever white part is there, that is our region of interest, and whatever black part is there, that black part is not our region of interest. So that black part is neglected before feeding to the higher level applications. If you see, the higher level applications are able to get these kind of data and these kind of data. If you will give these kind of data for in as an input to these application, these application may disturb because of this background information. But if you provide these uh, data to, like, input data to that automated application, so in that case we are able to detect the objects, means like we are able to get the information about the moving objects only. So that researchers started working on moving object segmentation task. So I will, means like, in that case, how that accuracy, or how that means like whatever region of interest we have segmented, how that is estimated, that I'm showing here. In that case, they are using precision recall and f measure, and that precision recall f measure is measured in terms of true positive, true negative, false positive, and false positive, false negative. So these are the cases for false positive, false negative, for different scenarios. So this is all about the evaluation measure used for moving object segmentation. If anyone having doubt, please raise the, or it will be discussed after the session. So so this is the, like, evaluation measure for moving object segmentation task. And experimental data, when this research started, and that in the, when that data is like for deep learning based algorithm, or for any kind of algorithm, we need to analyze the accuracy for that particular algorithm. To analyze the accuracy, uh, researchers started developing the database, that is a CDNet 2014. This is one of the famous database for moving object segmentation. Here, this is the input, and this is the ground truth they have marked, means like they have provided for experimental analysis, means like, where whatever we are doing here, this is the our output, and this is the ground truth, means like we are analyzing the things with respect to estimated output, and like provided ground truth for the experimental analysis. So this is one of the database. Next database is a Leicester database, and database 2016. So these are the, like, many types of databases they have provided for experimental analysis. It's like various researchers having developed the various databases with respect to various kind of limitation or kind of challenges. So now I would like to discuss the some existing methods. When this research started, background based method developed, means like how that background subtraction based method is developed is like, I will explain. Suppose we have one video. From that one video, one video, for that entire video, we will estimate one background, means like with the help of some handcrafted base, or average mean, or average max, whatever you want to perform the mathematical, and we will estimate the one background. And from that background, we will estimate, like, the foreground, means like how that background will foreground will be foreground is estimated, is like we will take the simple pixel wise subtraction between, like, estimated background and whatever current frames are coming. So these are the learning background based technique. And next one is the uh, background learning based method. So in this case, whatever initial frames are there, from that initial frames background is estimated, and from that estimated background and current frame, it will be provided to CNN. It's like deep learning architecture to get the foreground segmentation. Reference frame based method. So these are the different kinds of method that researchers develop for this, like, scene dependent frame to frame learning. When this deep learning based era started, that time, instead of estimating the background for entire video and then subtraction, researchers started developing the algorithm for directly for the segmentation, means like whenever RGB frame is coming, from that RGB frame we will get the like background foreground information, like this target mask. So this is all about the discussion. So now we will cover one small architecture details. Or anyone having doubt? Hello, hello.
Yes, sir. So I think they have written on the chat box, so we will take it later.
Okay, okay, okay. No problem. Thank you. Okay. So, so this is all about the existing method, about discussion about existing method.
Sir,
So now, yeah.
your screen sharing, I think it is stopped. Could you again share it?
Oh, okay, okay. Just a minute. I think screen is visible now.
Yes, yes.
Yeah. So these are discussion about the existing method. Now we will discuss the like what are algorithm we propose for object segmentation task. So next one is that like instead of processing the bunch of frames, so instead of processing the bunch of frame in a single encoder, they are like parallel processing. Means like from each frame we will learn the data independently and we will merge that data. Why to merge? Because one major thing whenever we are doing the any kind of research uh, in deep learning or in video based application, we need to consider the temporal consistency. So temporal consistency nothing but how the things are changing from one frame to the another frame. Means like suppose in teeth frame some objects is at x location, so that object will wherever it will be there in next frame, that we need to predict or we need to maintain the uh, uh, like consistency between these two. Means like there should not be any abrupt change in between the two consecutive frames. That is the one of the challenge. And next one is the motion between two consecutive frames. If you see here, t minus one frame and teeth frame is very means like very what we can say, there is no drastic change between these two frames. If you see, these are the two consecutive frames. From these two consecutive frames, we are not able to justify the difference between these two frames. So if we will take, suppose we are doing the segmentation for entire video and we have teeth frame object, teeth frame segmentation mask, which is estimated from our algorithm. That mask is used as a feedback to the current frame. Means like t plus 1 frame or t plus 2 frame, or it means like in future frames. So how that mask is used for experimental analysis, that I will show in next slide. So this is the our proposed solution. Here what we did means like suppose three frames are there, t minus 1 and t minus 2. From these three frames we have processed these three frames parallelly. Here, instead of processing these frame in one encoder or two decoder, we have processed the feature. We have processed the frame parallelly because we learn the space. We learn the features from first from respective frame, and from that respective frame merged feature means like independently learned features are merged in this block. So what this block is do, that I will explain in next slide. Further I will explain like this. These are the encoder decoder architecture. In that encoder decoder architecture, these three frames are used with the help of four encoder blocks, and parallelly that optical flow also is estimated, and from that optical flow we will get the some rigid information about the uh, uh, motion. And from that merged option means like these features are merged. Means like if you see here, this is the optical flow based feature and this is the feature from previous frame. Means suppose we are processing t frame, so we have output of t minus 1 frame. So here the t minus 1 frame output is provided as a feedback to the encoder block. So these are all kind of features are merged. Similarly, at each encoder level, we have merged the feature maps, and this is the decoder architecture. If you see this one, this is the decoder architecture. This one. So and this is all part about the encoder of the each feature map. Okay. So this is all about the encoder decoder architecture. And while decoding the case, we have provided the feature map from this recurrent age aggregation model. What this recurrent age aggregation model will do, I will show here. So this is our proposed recurrent age aggregation model. So here, these are the features from previous frame. These are the features from current frame, and this is like t means like t minus 1 and t minus 2. Okay, so these are the frames, these are the feature maps. That feature maps are subtracted from each other, and after subtraction, what kind of feature maps we are able to extract, this is the feature maps of that respective block. If you see, this is our region of interest for this frame. But if you are able to see this down one, so here also we are able to highlight that particular region of interest. Means like here we are suppressing the background information and we are able to extract the current means like foreground information. So this is our major motivation in this algorithm. So to provide the age information to the decoder block so that it will estimate the accurate or very fine age output for the segmentation. So this is all about the proposed solution for object segmentation. So this is the like training in training details. Generally, it is trained like any object segmentation algorithm are trained between video wise. Means like suppose we have one video. From that one video, initial 70% frames are used for training, and remaining 20% frame are used for, or 30% frame are used for testing purpose. So this is the in general practice. But with this practice, if you see, if I'm training one algorithm on one x data, one x input, and I'm expecting that model will give the output for y video also. So this is not possible, because we are saying that if you we are feeding one thing to the network and we are expecting the output from another thing. So this is a like cross database training. So we train our algorithm in different ways. Means like global training is like from each video some frames used for training and some frames are used for testing. So this is a common training testing technique in object segmentation. Similarly, in disjoint training testing, videos are divided. Means like suppose one video is there from sorry, two videos are there. Two from that two videos, one video will be used for training and another video will be used for testing. It's a disjoint training testing technique. Similarly, it's a cross database training testing. So this is a cross database, means like one database will be used for training and another database will be used for testing purpose. So this is all about the training testing technique and the result analysis. If you see, these are the quantity measures in terms of average F measure. So if you want like more result analysis, you can refer that paper. So in that paper, detailed elaborated results analysis are given with respect to existing methods. So this is a disjoint training, and then these two databases are used for disjoint training. This one is a local, means like frames are separated from each video. Some frames are separated for training and some frames are separated for testing. Similarly, for Leicester database, it's like a cross, means like whatever model we are trained for CDNet 2014, that model is tested on cross database. And what is mean by transfer? Means like transfer learning concept we have used. That model is trained for CDNet 2014, and that model is fine-tuned on some frames of AGVS database. That is a kind of transfer learning. So this is a quantitative analysis, and next one is a qualitative analysis. If you see here, our algorithm is able to give the accurate output as similar to ground truth. Okay, so this is all about the this is the result analysis with respect to disjoint training. So this is the estimated output from our method. Okay, and these are the ground truths. So this is if you see, like we are able to segment the ground truth, like we are able to segment the objects as much similar to the ground truth. Similarly, for global training testing analysis, if you see, these are the results for our method, and so this is all about the cross database training testing and this fine tuning base, means like transfer learning base. And one more thing, we done the evaluation study also, because any research work we are in any research, whenever we are proposing some module, that module should be analyzed the if that module should be analyzed with respect to result analysis. Means like what kind of feedback or what kind of features that module is able to provide for that respective module or respective algorithm. Similarly, here we have done the same case. Means like object optical flow based feature without feedback, with feedback, means like without feedback of previous frame features, with feedback of previous frame next frame features, like this. With recurrent edge aggregation module, without recurrent edge aggregation module. Similarly, fusion of like M feature, R feature, means like M feature is MFIT is a optical flow based feature. RFIT is a previous frame decoder features. Means like all kind of this analysis should be should be done to prove the proposed things. I am proposing one thing to extract the edge, but how that things will be proved means like if you see a recurrent edge aggregation module in last, how that edge aggregation module is working fine. If you see this accuracy and this one accuracy, there is a drastic change in the accuracy. So this is we need to prove for any result, means like any research work, whenever we are doing the literature or whenever we are doing the result analysis, that we need to provide evaluation study with respect to the proposed model. So we have done this. So in this case, like if you I will conclude here, like it is observed that the proposed inherent recurrent correlation learning based module is proposed for neural segmentation. Experimental analysis carried out for training testing techniques depending upon the global disjoint cross and transfer learning based configuration. And from result analysis, it is evident that the proposed network performs the existing method. However, whenever we are proposing any algorithm for any kind of application, there is some kind of limitation. If you see what are the limitations of object detection, if you see, so this is the limitation of object segmentation or object detection. If you see for data, whenever data is clear, so that time that object detection or object segmentation algorithm will perform better. It's like it will detect the or it will segment the all kind of objects. But what will happen if same data is degraded by some weathers? So this is the case when same algorithm will perform the object detection on like that same means like same algorithm is performed on this. So what kind of object detection will get like this? Will get this kind of object detection. But what about these kind of portions? So these portions we are missing to detect the objects. So this is the limitation of object segmentation. So researchers started working on restoration, means like restoring the things what are the degraded. After that, they will perform the object segmentation or object detection. So this is the limitation that we I found out in terms of object segmentation task. So but if you see these degraded situation, very bad incidents are happening nowadays because of bad weather. Means like for hazy data, for rainy data, it's like because of these bad weathers these kind of incidents are happening. So these restoration or whatever smart algorithms, smart techniques we are using for automated system, that is able to neglect the weather degraded effect and able to perform the required things. It's like decision like object detection or like whatever kind of expectation or whatever kind of expecting outputs we are expecting from that module, that kind of that kind of output we should get. So this is the like incident due to bad weather. So what kind of bad weathers are present? These are the hazy weather conditions. Similarly, for this is the rainy weather conditions. Similarly, it is a snowy weather condition. So these are the possible weather conditions that generally appeared in our real world challenges or real world system. Means like whenever we are providing any surveillance system in like day and night time for like rain case, snow case, haze case. Similarly for like traffic monitoring in weather degraded condition. So this is the like kind of different kind of real world weather degradation. So now what kind of algorithms are used to remove these kind of degradations to perform the better with automated applications. So this is like one of the prior model based. That is the prior model means like along with the dehazing, we will perform dehazing with the help of depth map. If you see how what kind of relation is there for depth map and haze. If you see this kind of portion here and this, okay. So here depth is more, so that's why haze is also more. If you see this portion here, depth is less, that's why haze means like haze is less. That's why depth also because it is directly proportional to depth. Whenever depth is more, that haze effect will appear as a more. So to remove the haze part along with the RGB hazy image, researchers are providing the depth map also. It's like this is the depth map. Next one is the rain map. Similarly, if you see along with the RGB rainy image, they are providing the rain sticks for the experimental analysis or for the proposed algorithm. So this is all about the uh, uh, prior based model. So when this deep learning era started, that time that prior based model has heavy limitation. We need to provide the prior information, means like depth or rain sticks or snow sticks information. But when this deep learning era started, that deep learning era removed that prior based model with the help of instead of processing the all the frames, like sorry, along with the prior information, they are processing only the RGB frame. So in that, similarly for hazy, this is snowy, this is the hazy, this is the rainy case. But if you see this last output is very complicated. Here we are able to see some rain part also there, some haze part also there, and some kind of snow also there. If you see this is like that jacket on, like that man jacket, that kind of snow information also present. So what we will do with this? So whenever this kind of complicated case will come, so in that case, if you see degradation learning, means like sequential degradation learning is happening. Means like one time we will remove the haze, second time we will remove the rain, and third time we will remove the snow. So, but it will be computationally complex because is a pre-processing step for object detection or object segmentation. If pre-processing step itself is taking more time, so that will overall process will be lagging. Means like overall process will be delayed. So this is the limited and this is the some limitation with respect to existing algorithms. So with to handle the like problem of sequential degradation learning or computational complexity, we propose some algorithm. So brief overview of this restoration kind of case we will see here. Whenever snowy image is there, that we will use the de-snowing algorithm. Whenever rainy image is there, we will use the de-raining algorithm. Similarly for DAC. But what will happen when this complicated situation will come? So in this case, we will perform dehazing followed by de-raining followed by de-snowing, and we will get this kind of algorithm. So, but here problem is that computational complexity, training data requirement, and sequential data learning. Training data requirement means any deep learning based algorithm in supervised case, we need to provide the ground truth.
Hello? Hello? Hello?
So this is so this is the case. These are the challenges whenever like computational complexity or training data requirement will come. So just a minute, I will take one call. Hello. Yes. Yes. So this is this is the problem with like existing restoration technique. So what like and one more thing like trained data requirement, how that supervised learning algorithm will be trained, because for real world case we are not able to capture the clean information. Means like suppose now rainy case is there or snowy case is there, for that respective picture we are not able to capture the clean data. So researchers started developing the synthetic data for experimental analysis. So for hazy case, we are using this mathematical function, and in that mathematical function, this is the input image, this is the transmission map, that what we have discussed about the depth map, and this is the real world hazy image. This real world hazy image used to estimate the EA parameter. So depending upon that A parameter, that kind of haze will be formed. Okay, this is a haze form. So if we are changing the value of A, if you see here, we kept the value A is a point 0.8, point 0.8, point 0.8. But if you see the value, we are changing from some points. So that kind of haze, whatever haze we are generating, that haze information or haze color is changing. So atmospheric like scattering effect, like that A value will be used to generate the different kind of hazy effect. So this is the synthetic hazy generation process. Similarly, for rainy case, we are using the along with this transmission map. We'll use the rain stick information. As snowy case also we will use this. So, but how this synthetic data and real world data is different as compared to the like these are the like first one. This is the real world data and this is a synthetic data. Sorry, it's exactly reverse. If you see the rain stick information, how we are generated synthetically and how it looking as a real world. So there is a domain gap between synthetic data and real world data. So this is the one of the major limitation we can say with for generation of synthetic data. So this is the, all about the data generation. Next one is the issue of sequential learning degradation. So one is in unified model also, in suppose first batch is there, first batch we are giving the hazy image, next batch we are giving the rainy image, third batch we are giving the snow image. But what will happen when this complicated situation will come? In this case complicated, I am saying here, if you see this part here, hazy data is there. If you see this part here, rain data is there. But if you see this like code part here, we will feel like it is a some kind of snowy data. So in this case, how that unified train model with the batch wise sequential learning is face this issue when at a time need to handle the three different kind of degradations. So this is the some of the challenges for existing algorithms. And in this we have proposed one algorithm. So in this algorithm, if you see this one is like input image is translated to d1 d2 like sorry id1 id2 id3. Here id1 id2 id3 are generated to make the restoration network weather invariant. Weather invariant means whatever data we are getting, whatever degradations are present in the input image, to make that restoration network uh, means like we will not bother about the what kind of degradations are present. So to do this, we have done some data augmentation, but data augmentation in terms of degradations. We can say ID1 is a hazy data, ID2 is a rainy data, and ID3 is a snowy data. So from this image, we have generated these three different images, and these three different images are used for restoration of this, means like restoration architecture. So in this restoration architecture, what we done is like four different encoders are used, and from that differently learned features are merged in this module, proposed PMDA module, like progressive multi-domain deformable alignment module. So this is all about the generational architecture. And I think GAN based approaches are known to all the volunteers. So this is a generator architecture in the GAN system. Means like discriminator, we are not doing anything. This is the generator. We are keeping this module as a generator for that particular module, particular restoration architecture. So this is the proposed solution. And how we done this domain translation, that I will explain in this slide. Okay, so here input image is there, that input image is transferred to this kind of degradation. If here if we are able to see this is the rainy data, and from that rainy data we are able to generate the snowy data with the help of training. Means like any input image will be transferred to haze, will be transferred to rain, and will be transferred to snow. So what happened with this case, we will get all kind of possible degradation at a time in a one batch to train the restoration architecture. So with this application or with this motivation, we assume that this kind of algorithm will give better performance in real world case. So that how that performance will be achieved in real world case, we will see. So this is the domain translation. And like here we have proposed this module is like MFE, multi attentive feature extraction. And if you see the how that multi-attentive feature extraction is working, here input without multi-attentive feature extraction and with multi-attentive feature extraction. So with multi-attentive feature extraction, we are able to get the good degraded data. Okay, so getting good degraded data or getting the degraded data with respect to real world is very challenging. So we got this, and this means like any image data, like any data will be transferred to like three different domain, and that different domains means like if you see here, this is a hazy data, but that from that hazy data we are able to generate three different degradations: haze, rain, and snow. Similarly, for rainy image we are able to generate haze, snow, and rain. Sorry, haze, rain, snow. Similarly, for snowy, from snowy data we are able to generate the three different degradations. So these are the sample results of domain translation, and these domain translation will be used here as input. Okay, and this is the our restoration architecture. Means like restoration generator. Means like GAN based system, we are using the we propose the generator architecture, and this controller is kept as a similar to that respective paper. So this is the restoration architecture. In this restoration architecture, we propose this progressive multi-domain deformal alignment module. In this, we are giving four different inputs here, like domain 3 input, domain 2 input, domain 1 input, and input image features. So from that feature maps, we are doing the splitting of the feature maps into groups. So how this feature like grouping, why this grouping is done, that I will explain first. Because suppose we are doing the multi-scale convolution. It's like suppose we have 16 channels and we want to do the multi-scale convolution with 3 by 3, 5 by 5, 7 by 7. So instead of processing these 16 channels, we divided these 16 channels into groups. So what will happen? First group will be performed 3 by 3. Second group will perform the 5 by 5. Third group will perform 7 by 7. So with this, like group wise multi-scale convolution will reduce the overall computational burden. So with this, we are able to manage the number of parameters in limited case, or limited number of parameters we are able to manage. And this is performed with respect to different alignment of feature maps. So this is alignment like snow, haze, rain, rain, snow, haze, and haze, rain, snow. So this is the kind of alignment models we have used alignment orders. And this is the, like we can say, this is the decoder block. In this decoder block, X here, if you see this one in this is the previous decoder features, and this is the PMDA features, like progressively modulated features we are able to provide here. So this is all about the restoration module. And training details, we have trained the domain translation separately and restoration separately. So this is all about the evaluation study about the results, means like baseline, independent feature learning, like progressive module, how it is working, like cascaded multi-head attention, how it is working. So this is evaluation study, and whatever assumption we done for this case that it will perform good on real world, that is happening here. If you see, these are the existing methods, and these are the our results. If you see this is our results. So in our results, we are able to restore, or we are able to remove the present degraded situation in the input image as compared to the existing method. So whatever assumption we done for, like it will give the good results for real world case, that is happening here. And similarly, if you see cross database training testing, means like whatever model is trained for daytime, that model is tested for nighttime data restoration. So we are able to get the good restoration result in nighttime case also. So with like it's like whatever challenges are there, like for day as well as nighttime, is covered with the help of this algorithm. So applications, I just now discussed about the object detection. So what will happen when this object detection is performed on pre-processed image of proposed method? So this is algorithm, this is analysis. If you are able to see here that objects are detected very properly, here also that object is detected more, that object is not detected anywhere in the algorithm. Similarly, application of the proposed method here for depth estimation. So this is all about the applications. Now I will conclude here. Like first, whether invariant representation learning algorithm is proposed, whether indirect representation is achieved via domain translation, and PMDA and CMA module are proposed for effective restoration, and real world analysis is provided on real world data as well as synthetic benchmark databases. So here are some limitations of current video restoration technique, like temporal consistency, unified model, complexity, or some of the like all weather activity recognition, anomaly detection, object tracking algorithms. So these are the like some limitations. So thank you for listening me. And if anyone having some doubt, you can visit my GitHub page for more details. Yeah, it's done from my side.
Uh, Thank you very much, sir, for your wonderful session. So, a lot of things you have highlighted, like the real-time challenges, like in object detection or something like yeah. So, participants, if you have any questions, so you may ask. So, I think, sir, there are some questions on the chat box. Could you see?
Yeah. First one is that how the true positive and false positive and negative values look like. Is it number or pixel values? So generally it is a number, but it will be calculated in each. It is calculated for each pixel. Means like for suppose one frame, how many true positives are there, how many true negatives are there. That will be like it is a number. It is not a pixel values, but with respect to pixel value it is estimated. Means like to get the how many true positive, we need to match the pixel values. And next question is that can sir, can you explain the operation of deformable convolution layer and what is the main purpose of this layer in the proposed architecture? Generally in convolution case we are using the fixed patch without any weights or without any gradients or without any like neighborhood information. In normal convolution we use 3 by 3 convolution, but in normal 3 by 3 convolution we are using simple 3 by 3 patch. But in deformable convolution we will get some weights for that pixel locations, and that weights and along with that kernel weights it is multiplied. So this is a major difference between deformable convolution and normal convolution. So in our case we use this deformable convolution to align the feature maps. Means like suppose we have two different feature maps, how to align these two different feature maps, because for same location we are merging these two feature maps. So while merging these two feature maps we use the deformable convolution.
Sir, can I ask one question?
Yeah, rather, you may ask.
Yes, yes, sir. Sir, so in image restoration, we just go for the convolution and deconvolution operation. Two operations are there.
Yeah.
Sir, what for this deconvolution is using?
No, your voice is not
Voice
clear.
very low. So, could you write on the chat box?
Yes, sir, yes, sir, sure.
Now you are audible clear.
Yeah, you can ask.
Sir, I mean to say, while image restoration process is there convolution plus deconvolution.
Yeah, it's like we have to use like encoder and decoder. Means like
Yes, sir.
convolution and
Encoder.
deconvolution.
Yes, encoder and decoder. And where we are using deformable convolution at the encoder part or decoder part?
Yeah, we, at encoder part, because in encoder part we are processing four different feature maps. To align these feature maps we are using the deformable convolution.
So when we are using the deformable convolution, so it's a kind of group convolution. It is
Yeah,
dynamically generating the kernels,
yeah.
and we are learning those kernels.
Yes.
So there will not be any problem of resolution. Like we have in
No,
transformers, we have the resolution problem. So deformable convolution will overcome that resolution problem.
no. There is no problem of resolution in deformable.
Okay. Okay, sir. Thank you.
Okay.
Audience, any other questions? Dr. Prashant, I have one question.
Yeah.
So yeah, so did you also try any domain adaptation approach for reducing the gap between like clean images and some foggy images? So for in
Human
your
adaptation, no, but in existing literature, there is a approach of knowledge distillation kind, but domain adaptation we have used for restoration. Means
okay.
like how this daytime train model will be adapted
Mhm.
for the case where the very limited data we have.
Mhm.
So in that case, we have adapted with the help of meta learning concept.
Okay, okay.
Yeah.
So any other questions?
Sir, hello.
Yeah.
Can you
Yeah.
hear me?
Yes,
Yes.
Nitin.
Um, in the like you were saying, you're generating synthetically these haze and some rain and these like kind of noises to the data, and
Yeah.
you're trying to restore the original image
Yeah.
using some GAN or something, right?
Yeah. Yeah.
Um, and also you said like there is the domain gap between the real generated and the synthetic images. Like,
Yes.
uh,
Yes.
uh, are you using some um, what is actually going on there? Like once go to that slide, I have to look at it.
Which slide number? Just I will share the screen. Which slide should I go? This domain translation one.
Yes, once.
This one you are saying
Mm, the once go before.
before
Yeah, 37, 36.
this one or this one.
Okay, yes, sir. Once, once once give a abstract office, I was not able to listen this. Once again, can you explain this?
Yeah, yeah. Here, what we are doing, like whenever any input image is coming, that input image is translated to three different domains like ID1, ID2, and ID3. This ID1 is nothing but hazy, ID2 is nothing but rainy, and ID3 is nothing but snowy. So these three different degradations we are generating with the help of domain translation, and these degradation along with input image. If you see this part, it's like here, if you see this, or sorry, so if you see this part here, we are providing these domain translated images and I for restoration, and here we are performing independent feature learning. Means from hazy data features will be learned, for rainy data features will be learned, and snowy data features will be learned, and from that learned features we are we are getting the common part. Because if you see in these three images or in these four images, degradations are different, but whatever content we want to restore, that content is same. So our restoration architecture, we learn the similar content from that all the different domains or different input images.
Yeah, like it's like a unified
Yeah,
thing.
yeah, unified.
But these are like ID3, ID2, and ID1. These are like synthetic data generation techniques, like on the image.
Synthetic data generation through learning process. It's not a mathematical process.
Okay, but now after in the results you have tested on the real images to restore back to less hazy and less rainy.
Mhm.
How are they performing well? Means there is a domain gap between the synthetic and the real. That how
Yeah,
are you
yeah.
testing?
Actually, we are means like here we are using while generating this degradation, we are using the real world loss, means like real world image loss, to generate kind of real world degradations. That concept is like far, like it will take time to how we are generating the data in real world. Means like while domain translation network training, we use some real world data for training purpose to generate the real world degradation. So with that, we proved uh, there is a less domain gap between synthetically generated data and our generated data as compared
Okay,
to the real world.
Okay. While generating synthetic data generation only, you're using some kind of noise from the real data.
Yeah,
Okay. Okay.
exactly,
Got it.
exactly.
Yes. Some request of the title of the paper in chatbot, chat
Uh,
box.
yeah, I will just a minute. Huh? I will stop. Even I like you can visit my GitHub page actually. There, here I provided all the is like here in this yeah, in this GitHub page that paper is available. You can refer that paper. So you will get the more details in that. Yeah. Any doubt? Other?
I think there is no questions.
Okay.
So thank you, Prashant sir, for your wonderful session.
Yeah.
Yeah. So I think now we can close the session.
Yeah. Sure. Thank you.
Thank you. Thank you.
Okay. Okay. Bye.